So with that, we will move on to our final speaker of the session. Benjamin, why don't you just go ahead and take it away?
Sounds good. Is my screen showing up okay? Cool.
Looks good.
Great. Hello, my name is Ben Pedigo. I'm a PhD student in the Neurodata Lab at Johns Hopkins, and I'm excited to tell you about my work on a statistical analysis of bilateral symmetry in an insect brain connectome. So first off, why are we looking at connectomes in the first place? I think there are many interesting connectome questions that all sort of revolve around or require some notion of comparison. So just as a few examples, if we wanted to understand how connectomes change across evolution, we would want to, say, measure multiple connectomes from different taxa and then have some way of comparing them. Or if we wanted to understand how connectomes change across development within a single organism, we would want to, again, collect multiple connectomes at different stages of development, and then, again, make some sort of rigorous comparison between them. Likewise for, say, genetic perturbations and connectivity. So for the purposes of this talk, we're going to focus on just one connectome, that of the larval Drosophila brain. I won't talk too much about this data set because Michael Winding, who led the data collection effort, will be talking about it tomorrow. I encourage you to check that out. But crucially, what's most important for us today is that both hemispheres of this animal's brain have been reconstructed using electron microscopy and then manual tracing of that brain. So as I alluded to in the title, the question that we're going to focus on for this data set is simply, are the left and the right sides of this connectome the same? And this is a question that has been brought up a lot in various ways in connectomics, and I'll talk about how we're approaching it as a statistical hypothesis test. So if we had been handed two data sets that were just data on the real line, say the heights of people in two different groups, then what we would want to do is run something called a two-sample test. And typically what you would do is say that your data Y1 comes from some distribution, your data Y2 comes from some potentially different distribution, and then you're essentially testing the null hypothesis that those distributions are the same versus the alternative that they're different. So very simple, you could run something, say, like a t-test would be an example of a two-sample test. But what we have is two networks. So we essentially want a two-network sample test. And for simplicity, I'm going to consider both networks to be directed but unweighted, so just binary, is there an edge or not? And then again, just for simplicity, we'll just look at the sort of subgraph on the left side of the brain, just the connections from the left to the left, from the right to the right, and we're going to ignore connections across hemispheres. So similar to what I just described, we're going to use this approach where we consider the adjacency matrix on the left, AL, to come from some distribution, likewise on the right. And again, we're just asking whether or not those distributions are the same. So to do that, we'll have to talk about a few different ways that we can think of a distribution for a network A, and I'll present a few of those and then describe how they lead to different tests. So arguably the simplest model of a network that you could use is the Erdos-Rainey model. It basically just says that each potential edge is generated independently with the same connection probability for each edge. So you could write that as the probability of an edge going from I to j is just equal to p, and p is the same for all edges. So in terms of comparing these models, then, since we just have this one parameter, all that we have to do is compare this probability between the left and the right hemispheres. And so that's what I'm plotting on the right side. You see the estimated probability is slightly lower on the left hemisphere than on the right. And if you run a statistical test, in this case, Fisher's exact test to say whether or not those two are significantly different, you get a very low p-value, lower than 10 to the negative 23. So in some sense, our job is done. The talk could be over. We've already said that we sort of rejected this null hypothesis of bilateral symmetry. But you could argue that, this is probably not what neuroscientists mean when they talk about the symmetry between the left and the right sides of the brain. and I would agree with you. So nevertheless, we're going to proceed and look at a few other different tests as well as how this result will affect them. So the next slightly more complicated model that we could use is called the stochastic block model. And what this model cares about really is binning my nodes into a bunch of different groups and then looking at connection probabilities among those groups. So the probability of an edge going from I to J is going to be indexed by this matrix B. So if I have K different groups, I'm going to have a K by K matrix B, and that matrix is just going to tell me what is the probability of a node in one of these groups connecting to any other node in some other group. That these vectors, tau I and tau J, just assign each of my nodes to one of those groups. This is a commonly used statistical model for networks that's been used a lot, especially in the social network literature. For now, I'm just going to use some sort of broad cell type labels from this data set that Michael will probably tell you more about tomorrow as my labels for groups for each neuron. So now with that set up, under this model, all that we have to do to compare these two networks is look at the group-to-group connection probabilities that are stored in these matrices B. The way that we do that is just by running a bunch of different probability comparisons between each element in these matrices. So for instance, this is showing a heat map of p-values that we get from doing all k squared of these different comparisons. So for instance, this element here is looking at the comparison between these CN to CN neuron connections between the left and the right hemispheres. And what you see is that there are 5 different significant comparisons after correcting for multiple comparisons. We can also combine all of these p-values using something called Fisher's method to give us sort of an overall sense for this null hypothesis that I've written here. And we get a p-value, again, that's fairly small. It's less than 10 to the -4th. So long story short, what this is saying is that, again, under this stochastic block model, which cares about connection probabilities between cell types, we are rejecting this null hypothesis of bilateral symmetry. But in some sense, that's not surprising, given what I've already told you about the difference in density. So we already saw that even under the simplest model, these two networks were different. So perhaps we now think that maybe the connection probabilities on the left side are just some scaled version of the connection probabilities on the right. And we can write that now as a new hypothesis, null hypothesis here, where we're saying that B left is some scaled version of B right, where C is just this density adjusting constant to account for what I just said. So there are a few different ways you could run a test using this correction, and I think the simplest and most intuitive one that I'm showing here is to just randomly subsample edges from the denser network, make it match the density of the network on the left, and then rerun this test. But of course, we do that many times. Here I'm just showing what happens if we run that test 100 different times with 100 different subsamples. And you see that all of the p-values now are pretty high. They're all greater than 0.6. So after doing this adjustment for a difference in density, now we're failing to reject this null hypothesis here. So moving on to one more complicated model here. This is called the random dot product graph model, which you can sort of think of as a more general model than the stochastic block model. What this says is that the probability of an edge going from I to J is the dot product between some latent vectors xi and yj. So I essentially have latent vectors associated with each node in my network that are somehow governing the connectivity that I observe. And we have ways of inferring those parameters that are related to spectral embedding methods, if anyone is familiar with those. So further, we just assume that these sort of latent positions or latent vectors on the left and the right, again, they just come from some distributions, and those are just going to be multivariate distributions in D dimensions, where D is just whatever embedding dimension I chose to embed my network into. On the right, I'm plotting what that looks like for D equals 3. So remember now, each point in this plot represents a individual neuron, and I'm just showing this three-dimensional structure by plotting each pair of dimensions. And what you see in this plot is that the parameters for the left and the right look quite similar, and indeed, if you run a multivariate two-sample test, you get a p-value that's quite high, somewhere around 1, and this is pretty consistent across any choice of your embedding dimension D. So for this test, more or less, the long story short is that we're failing to reject the null hypothesis here. So one last thing I want to highlight before I wrap up is, we're not just interested in looking at these tests and what they show us on the data that we have, but we also want to make sure that we can detect differences when we know they exist, for all of the reasons that I listed at the beginning of the talk. So what we're doing here is making 2 copies of our right hemisphere network. We can then apply some synthetic perturbation to one of those. So as an example here, I'm just shuffling all of the edges that are incident to some number of nodes. And then I can rerun this test and decide whether or not it picks up on that difference that I've just injected. So that's what this plot on the right is showing, where the x-axis is essentially the effect size. So as I move to the right, I'm perturbing this connectome more and more. And the y-axis is showing the p-values that I get from this test that I just described. So each of these lines is just perturbing a different group of neurons, but for all of them, you see this consistent trend that as I perturb the network more and more, my test is more and more able to detect those differences. So just to wrap up briefly, we talked about several different models that one could use to model each of these networks. I didn't have time to go into some of the others that we've looked at, but for the ones I've shown here, the Erdos-Ramey model basically told us that we should reject the null that the densities of the 2 networks are the same. And similarly, the stochastic block model test said that we can reject the idea that the cell type connection probabilities are the same. But if we added just this simple correction for the density to the stochastic block model test, we see that that difference more or less goes away. And this test based on the random dot product graph likewise also said that we fail to reject that the left and the right are different, at least under that model. So I think the key takeaway that I want to highlight here is that even though we started with a very, very simple question to ask of these 2 networks, the answer that you get totally depends on how you frame it as a statistical hypothesis test. That's not all that surprising because each of these models leads you to a different test, as we saw, and each of those tests is going to be sensitive to certain alternatives, but not others. I also want to point out, like we saw with this density correction case, if there's a difference that you think you might not care about, that needs to be explicitly accounted for when you do some sort of comparison like this. Otherwise, you could get a significant result that maybe you didn't want. So as I alluded to, we're working on adding many more tests to this framework, as well as studying how each of these tests performs under a bunch of different alternatives, more than just the one that I gave as an example. And my hope is that this can be a roadmap for future statistical comparisons of connectome networks for all of the reasons that I talked about at the beginning, like looking at differences in development, looking at differences across evolution, things like that. I'll briefly plug our Python package, Graspologic, that was used for most of this analysis, as well as this link here, which is basically like a preprint. So this is a Jupyter book where we have all of the code for the analysis I talked about today, as well as a lot more explanation if you're curious about more of the details than I had time for today. So many people to thank, all these awesome collaborators, as well as the organizers. Thank you so much. And if there's time, I can take questions, but I believe we might be running out of time here.
Thank you very much. This was great. And because we started your talk a little bit late, we've got time for quick questions if anybody has them. I don't see any extras in the Q&A box right now, so maybe I will take this opportunity to ask one very quick question, or kind of half comment question, which is, I thought that the result that the perturbations in different networks really have a very big effect on whether how many neurons you can perturb before you actually are able to detect the effect. So
totally.
what are your plans for how to take those kind of sub-network sensitivity or robustness to perturbation into account when you're doing some of these statistical tests? Does that make sense?
Kind of. I guess, are you asking...
like, are you going to be able to factorize like whether there is or is not an effect according to a particular statistical test by where that effect might be driven by in terms of these sub-networks?
So are you kind of asking whether these tests, whether you would be able to ascribe some, like this test is rejecting because of this particular part of the network? Is that?
Yeah, not necessarily as the tests are written now, but do you have plans to kind of think about how to do that in the future? Is that on the table?
Yeah, definitely. I mean, I think depending on what test you're running, they can be either not interpretable at all or like very clear. Like I think the SBM test where you're just using cell type groups that you already know is kind of clear, because if you see that this thing is significant, you sort of know what that means. For some of these more complicated tests, like the one based on the RDPG, it's a little bit more complicated, but there are a few ways to sort of look at the latent spaces that I showed you and ascribe a little bit of meaning to them. But yeah, I think that's absolutely on the table, and we definitely want these tests to be interpretable.
Fantastic. Well, I think that's probably all we've got time for today. Thank you very much to Ben and to all of our speakers. Really fun session, really enjoyed it. And I'll remind people, take a quick break to get a snack or use the restroom, because we'll be back in just about 7 minutes with our next main stage talk. So stick around or head over to Discord, do some flash talks, that kind of thing, and we'll see you at the next session. Thanks all. Bye-bye.